Welcome to Team Alpha Electronics Aquaponics Control System video demonstration. I'm Jesse Vault and I will begin our demonstration with a brief description of our system. We considered a solution to allowing families and individuals the opportunity to implement self-reliance in the form of home gardening. Until hydro and aquaponics developed, home gardening has been seasonal. Additionally, the tasks involved to keep up on home gardening can be extensive when it comes to time and expertise. We designed a solution for the year-round gardener utilizing aquaponics technology. With all of the factors to consider, we thought, let's design a system that monitors and adjusts the system according to user-defined settings, which would ultimately provide confidence to the gardener that their operation is functioning properly, and which would decrease the required time to maintain it. We thought about the factors involved and began our brainstorming from there. We used a data acquisition device, DAC for short, to interpret incoming environmental signals from sensors and probes. Those signals are processed by a personal computing device using a National Instruments LabVIEW program. Once processing and comparing are complete, output signals are generated through the USB DAC to control the system. We chose the National Instruments DAC device based on its compatibility with LabVIEW and the number of input and outputs we desired. The LabVIEW program was developed by Lisa, and I will now let her explain how that works.
Hi, my name is Lisa Snyder and I am the programmer for the Alpha Electronics Team Aquaponics system. This picture is a LabVIEW GUI interface that controls and reports our control system. On the left side of the GUI are the recordings from our 4 sensors. This is the section that reports what the temperature, oxygen, and ammonia probes are reading, as well as the flow meter. The middle section contains user-controllable set points for the system parameters. At any time, our customers can change these set points and they will be immediately reflected in the program operation. The lights in this section indicate if the actuators are active. The right panel of the GUI shows the current computer time and has clocks for controlling the grow light and feeder timer. The bottom portion of the controller is for the reporting feature of the GUI. It allows for a log of sensor values and email options, which can show a combination of alarms and log values. We use the National Instruments 6001 USB DAC controller to both read the sensors and activate the outputs. Each sensor was connected to a differential analog input. In order for the DAC to correctly read the sensor, each input channel had to be configured to create the correct parameter. The temperature, oxygen, and ammonia probes each output voltage, so they were configured to read voltage. The flow meter output a frequency in the form of a square wave, so that input for that sensor needed to be configured to read a waveform. For the outputs, we used the digital IOs. In order to do this, they needed to be configured as outputs. These outputs then would toggle between 0 volts and 3.3 volts, depending on the data that was written to that particular output. There are several portions to the program. The front panel interactive portion of the GUI is handled by 2 loops. One is the event handling loop and the other is the message handling loop. The event handling loop constantly polls whatever controls are set up on the front panel and detects when one of them changes state. When that happens, it creates a message which is then entered into the message queue. This message correlates to a particular state of the message handling loop, and that state is executed. Running simultaneously with the event and message handling loops is a loop for the clocks and timers. This loop keeps track of the current computer time and calculates if it is time for the feeder to be activated. If it is time, it then activates the outputs and calculates the next time the feeder needs to run. If the Run button on the front panel has been activated, the third loop in the program begins to run. This is where all of the sensors are being run, the calculations are being performed, and the actuators are being triggered. when it is appropriate for them to be. Also in this loop, the logging and email functions are being triggered when appropriate, and the next timing for these triggers are calculated. All in all, the LabVIEW platform with the 6001 USB DAC provided us with a lot of functionality that we were seeking. It had enough inputs and outputs for us to read multiple sensors and control multiple outputs. It allowed us to provide user-friendly, on-the-fly changeability to the consumer. It allows remote monitoring and control, not only through the email and logging functions, but also through the remote login. Thanks for your attention.
Each sensor was chosen in accordance to the needed compatibility for the control system subsystem. These sensors are the oxygen sensor, the ammonia sensor, the flow meter, and the temperature probe. As you can see, 3 of these were obtained by Atlas Scientific, and 1 was obtained by Vanair. Each sensor will be activated by the actuators to the specified accuracy per customer specs.
Hello, Jesse here again with the portion of the project I volunteered for, and that's the power subsystem. We needed a power subsystem since we had various voltages and components within our system. First, we knew that our control devices within the aquaponics system would be operating on 110 volts household power. Second, we would be controlling those devices with our DAC, which outputs a signal of 3.3 volts DC and low amperage. Additionally, our probes would need low voltage as well to perform their functions. With component isolation protection and signal drivability to consider, I knew the DAC output would not be enough to drive a relay to control our 110 volt side of the control device. I used my knowledge of converters, transistors, and relays to develop a subsystem which would enable our control system to provide its function. Once the power subsystem was complete, I created an instructional pictograph for Brandon and Michael to use for connection of the various power components and the power board within the control system. I'll now pass off to Brandon to explain a little about the enclosure.
During the assembly of the aquaponics control system, Team Alpha Electronics acquired a control panel for the system. Although this was the right size that we needed, there was some customization needed for all of the analog outputs of our 6001 DAC. Once the proper holes were drilled for the output, we inserted BNC connectors on the outside of the panel for ease of access. The unit was then sent to the other team member to finish his subsystem and create any additional customizations.
Hello, my name is Michael Ross from Alpha Electronics. My part of the project for the senior project was to build a control cabinet. I chose to go with a Hoffman box that was 16 by 14 by 6. This is a component that I'm familiar with. I use a lot of them in my professional life. And due to the application, the Hoffman box is not only substantial, but is waterproof, and as one of my teammates referred to it as bulletproof. Part of what I was charged with doing for the project was using some DIN rail to provide a means of terminating all of our inputs and outputs. I used an Allen Bradley DIN rail with Allen Bradley terminals. I also mounted the bus for our ground, the bus for our neutral, the bus for our hot, 120 volts. I also mounted our USB 6001 as well as the power PCB board coming off of our outputs. I also began to tie in the BNC connectors for some of our inputs. I drilled and mounted all of our outlets for are field devices, which can be seen on the bottom right hand corner of the box. After I wired everything in, I began testing, doing some preliminary testing for our inputs for the oxygen sensor and the temperature sensor, which at that point were working fairly well but did need some tweaking, which was done later by Jesse Vault. I also tested all the outputs. I simulated the inputs and tested all of the outputs, which can be seen on the bottom right hand corner for our field devices such as the pumps, filters, heaters, etc. Thank you.
This is the live demonstration of Team Alpha Electronics aquaponics control system. We've got our PC connected to the USB directly into our enclosure. That's going to read and process any signals gathered by the National Instruments data acquisition device. The incoming data on the input side is measured through our various sensors and probes, which are implemented into our test subject here for measuring oxygen temperature, ammonia, and the flow meter that measures the pump flow, pumping the water through the plant system and back into the pond. So as you can see on our GUI, we're reading about 83 degrees with a flow of 4.68 gallons per minute, ammonia reading of 0.0108, and dissolved oxygen at about 67%. You take a look at the settings here. We have our temperature set at 70, minimum oxygen 0.5, ammonia 0.05, and our minimum flow at 2 gallons per minute. We're above that on all of these numbers, so therefore none of the indicator lights are on. We're set to feed here at 9:32 p.m. in 1 hour, so we must have just missed it. But our grow light setting is from 7 a.m. to 9 p.m. and the light indicator is on, and the rope lighter is my makeshift grow lighting for now. The log and email options are set to send data at those times. As we trigger the settings, we can see each actuator turn on as it should. And I'll just let it do its thing and pull while we adjust the settings, just to show how each facet will go ahead and change as it's compared. What you're seeing now is a shutdown so that we can get a dissolved oxygen and ammonia reading. And the reason we had to do a shutdown was because the pumps and things in the pond actually cause interference with those electron devices, such as the ammonia probe and the oxygen probe. So we go ahead and shut everything down for a few seconds, take our measurement, and then go ahead and turn it back on. So I've set these parameters way outside of what I know it should be running at. And we should see each of those start indicating. So the temperature should be at about 90 degrees. We're at about 85. The oxygen should be at 86 at a minimum. We're about 60. The ammonia should be no lower than negative 0.95. And the minimum flow from the pump should be no less than 5 gallons per minute. So we'll finish our shutdown reading mode, and we should see all of these actuators start triggering on. Now as they start comparing, we see the heater kicks on. You have backup oxygen. I don't know if you can see the bubbles in there now from our aerator. We have our backup filtration kicking on, because that indicates that our ammonia is too high. So those are carbon charcoal regular filters you would find in any fish tank. And once that level drops back down to an okay value, then that filter will shut off. And then we see that, oops, all of those actuators are engaged. Now anytime major adjustments are made, the system does go ahead and just shut down. This is all for demo purposes, but it'll take its readings and then it'll do its comparisons and then engage. So this shutdown process actually occurs when I tell it to, or periodically at 1 hour, 4 hour, 6 hour, or whatever settings we want it to. That's great to do all these adjustments and actually hear all the relays clicking around and sending signals over to the actuators. So our control device can actually be mounted to a wall or a table out of the way, and you can buy extensions for all the probes and sensors, so you can move this as far away as you want, or have a hub with 4 or 5 of them, depending on how big your operation is. And then I've got the USB can be as long as you want. I've got a 30-footer here, so I can have it connected to a desk that I have across the room. That way my PC's clear away from the water. But that's our demo, and our system's live, and fish are happy.